And before we dive in, let us go through some basics. So, what is a system? What do I mean when I'm talking about a system? So, a system can be basically anything that is it's sort of any part that can be taken out by something that we will call the environment. It doesn't matter that much which part is the system and which part is the environment, because we need to describe the both of them to an extent whenever we're starting to tackle a problem. And what we consider system, what we consider environment, what we consider subsystem, and the components of the system. Those are things that we need to clarify to ourselves when we're attacking any particular problem. So just an example, a rocket could be a system. It could have a subsystem, which is the propulsion system. A person could be a system with the circulatory system as the subsystem. A university could be a system, and a nation could be a system. We also have the global system in which the nation is embedded in. So these are sort of like systems embedded in systems always, and we need to decide how to what are the meaningful factors to take into account when we're starting to analyze any particular problem. And one thing we usually encounter when we analyze these systems is that they have a lot of detail. There's a lot of nuance in reality. So, for example, in this picture, first of all, this is not a person sitting on a pile of books. It's a picture of a person sitting on a pile of books, and that's of course, meaningful in itself, but the picture itself that represents the reality, it omits some features of reality and contains others. But when we look at the picture, there's a lot of detail still in that picture of the reality. And what we do when we try to comprehend this reality in some way is that we almost drive it through a filter that we observe it via these our personal histories, or learn the concepts and narratives we've learned, mental models or mathematical models if we are doing data analysis. And then we end up with something with a simplification that we can pass on to other people and tell other people like what is going on here. And this question, what is going on here, is very key. And that's usually one of the big issues that people encounter when they're starting to solve problems, is that they start from the solutions instead of starting to figure out what the problem actually is and what's going on in the problem. So we can then write up these research reports or policy briefs and produce data and make sense of the data in a distributed fashion with a lot of other people and stakeholders and communities and so forth, and interpret that collectively. But the thing is that whether this simplification that we see here is a reasonable simplification, because we can't take all of the reality. We need to do some simplification to the reality. Whether it's a reasonable simplification or not depends on whether it contains the meaningful details of the reality and meaningful details for the problem that we're trying to solve. So uh, if the important thing about the reality is that there is a person sitting, then this is a very like an excellent simplification. It describes all the important facets of sitting. So there is a person sitting, and you can see it and get it by just looking at the picture. But what if something else is important in that reality? What about if the important thing is reading, or worse yet, learning, or the education system, or something like this? Then this simplification of ours is just completely false. It doesn't represent the right part of the reality, and if we would use that for problem solving, we would go astray. And one common term to be that's been used is this the phrase "the map is not the terrain." So the terrain is the raw reality in all of its richness, and the map is the simplification that we make of it when we interpret the reality and we ask ourselves the question of what is going on here. And these two are not the same. And this is an obvious point, but it's very good to keep in mind. And this can be exemplified with this person who has taken out the best map they have available. If you remember, we spoke about the best map fallacy. And they're trying to make their way in the woods with a map of the world, which obviously they would be better off without any map. So just to think about, okay, so these caricatures of what can be different systems. So we already talked about rockets and other machines. They can be systems, even if they are very complicated systems, and that sometimes break unexpectedly, but still produce relatively stable and predictable behavior. And this getting to this point where they do that has taken a very, very long time of trying to refine and doing and being in error and doing things differently and so forth. And then we have other kinds of systems which might be said to have many, many components like these other systems that we talked about. But these components, instead of just being there and reacting, they also adapt and change their behavior according to how their neighboring components uh, act. And cities and ecosystems and social networks and people, they are sort of very different from these machine-like systems in that they contain these uh, co-evolving components, which means that they are they're constantly in flux. So they are moving instead of so if we would have a this rocket, for example, and we would build the rocket and we would uh, keep a tally of what was the environment where we kept built the rocket and what was the components that we needed and so forth. And so it would be very likely for someone else to look at our instructions and replicate the environment, and then get the same parts, and then use those parts to build the rocket that will look like ours. But if we do the same with a child, it is just completely impossible, because even raising one child in one way and thinking you would do the same for the next child, it's a common experience that something completely different comes about. And these, as I said, these systems that are on the right can be very complicated, but the systems on the left, we could call them complex. And in complex systems, this saying that the definition of insanity is doing the same thing over and over and expecting the different results. So this is apparently not really something that Albert Einstein has said, but it's often attributed to him. But this statement it works in the context of these complicated systems. But with a system that is constantly moving and flowing and fluxing and adapting, the definition of insanity could as well be doing the same thing over and over and expecting the same result to continue. And So if we think about one problem when we try to solve societal problems or analyze the data is that we usually or quite often what we see is that people take the idea of this sort of complicated system, and so they use it as a map, even though they are actually working in a complex environment. And so if we think about what could go wrong, so if you're in a complicated environment and you think you're in a complex environment, you may be doing things very sort of inefficiently. So you're moving slower, and you're keeping redundancies, and instead of trying to lean out all the so-called unnecessary uh, uh, weight, and so you would be slower and less efficient. But if you would be in a complex environment, and you would think that you are in a complicated environment, uh, that would actually lead to you making very bad decisions, and possibly uh, 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 leading to catastrophic results. So there's an asymmetry on what we think what we have maps of, and what the terrain could be, and we will delve deeper into this distinction between complicated and complex.